Today, we're diving into a really cool breakthrough in AI that's tackling one of the most frustrating things about it. It's speed. It's a new method called Learn2PD, and honestly, it could completely change how fast we get answers from our most powerful AI models.
I mean, you've totally felt this, right? You ask a super powerful AI a question, and you just watch it type out the answer. It feels slow. So why? Why can't it just give you the whole thing at once? That's the big question we're going to unpack.
Well, it really all comes down to a huge difference in how they work. See, most of the AI models we use today generate text one word at a time, kind of like a slow-motion domino chain. But what if they could just knock over all the dominoes at the same time? That's the secret to unlocking some truly incredible speed.
So to really get the solution, we've got to understand the problem first. And in the world of large language models, the main culprit, the big bad, has a name: the autoregressive bottleneck.
Okay, so this is how most models think right now. Autoregressive decoding means that every single new word, or token, can only be created after the one before it is already known. So the has to come first, then quick, then brown, and so on. This dependency creates a natural speed limit that you just can't get around. It's kind of like building a train track one piece at a time. You literally can't go any faster than you can lay down that next piece.
So if building one track at a time is just too slow, what's the alternative? Well, researchers have been working on a completely different way of doing things, and it comes from a class of models called diffusion LLMs, or dLLMs for short. Instead of writing a sentence word by word, a DLM starts with a sort of rough sketch of the entire sentence. Picture a page of blank, masked-out words. Then, in a bunch of steps, it just keeps refining that sketch, denoising it, filling in the blanks until the final clear text appears. And here's the crucial part: all the words get refined at the same time, in parallel.
So, parallel generation. That sounds amazing. Problem solved, right? Well, not so fast, because what the researchers found was that even these super advanced models had a massive, hidden inefficiency just lurking under the surface, holding them back.
And this, right here, brings us to the core insight of this entire study. The problem wasn't with the idea of parallel generation itself, but with all the wasteful, repetitive work the model was doing behind the scenes. So here's what was happening. The model would actually guess a word correctly, but because its own confidence wasn't 100%, it would erase it or remask it and then spend precious computation time figuring out the exact same word all over again. It was basically double-checking homework it had already aced.
Let's just walk through an example. In step 1, the model predicts the word deep. It's the right word. Perfect. But then, in step 2, its own internal logic makes it second-guess itself, so it just throws the word away and puts a blank mask there. Then, in step 3, it has to do all that work again to repredict deep. This is just pure wasted effort.
And just how bad was this problem? Get this, the researchers found that most words were being redecoded more than 10 times after they had already been predicted correctly. Can you imagine solving a math problem, getting the right answer, and then erasing it to do it 10 more times just to be sure? That's the insane level of waste we're talking about here.
Okay, so that's the problem, a pretty big one. Now let's talk about the incredibly clever solution they came up with, which they call Learn2PD. Their entire approach really started with this simple but really powerful question. Instead of having one rigid, dumb rule for deciding when a word is done, could they create a smart, flexible system that decides on a case-by-case basis?
And that is Learn2PD. It's a tiny little AI model that sits on top of the main one and acts like a smart supervisor. It just watches the main model work, and it learns to predict when a word is final. It's the thing that can say, yep, that one's good, lock it in, don't waste any more time on it. Or it might go, not so sure about that one, let's give it another pass.
And what's really amazing is just how practical this thing is. This smart supervisor isn't some giant, complex beast. It's a really simple little network that adds almost no slowdown at all. In fact, and this is wild, it only took the researchers 6 minutes to train. It's an unbelievably efficient fix for a massive inefficiency.
But hold on, because that wasn't the only source of waste they uncovered. It turns out that after the model finished writing its actual answer, it would often spend a huge amount of time just decoding the blank space or the padding that came after it.
Now, this is just staggering. In some cases, nearly 90% of the total computation time was being wasted on decoding useless padding after the real answer was already done. That's just mind-blowing.
So they brought in a second super simple mechanism called end-of-text prediction, or EoTP. It's brilliant. As soon as the model spits out that special little token that basically says, hey, I'm done, EoTP just cuts the power and stops the whole process. No more wasted cycles on empty space. It's that simple.
All right, so we've got a smart filter to stop the model from redoing correct work, and a simple off switch to stop it from decoding empty space. So what happens when you put them together? Let's check out the results, because this is where it gets really fun.
The result? An absolutely staggering 22.5 times speedup. And what's so crucial here is that this massive performance gain came with basically no drop in the quality of the answers. It's not just faster, it's just as smart.
And believe it or not, it gets even better. This method plays nice with other optimization techniques. So when they combine it with something called a KV cache, which is kind of a memory system to help the model not recalculate things, the speedup jumped to an incredible 57.5 times. These gains actually stack on top of each other.
I mean, just look at this chart. The original model is just chugging along at half a token per second. You add these new methods, and it leaps up to over 12. Then you combine it with the KV cache, and it is flying at over 31 tokens per second. The difference is just night and day.
So what's the big takeaway here? It's that by tackling two very specific kinds of wasted work, redecoding words that are already right and decoding empty padding, this research delivers a monumental speedup. But even more importantly, it makes these powerful parallel models, these LLMs, a truly practical option for the real world.
And that really is the bottom line. This isn't just some small tweak we're talking about. It's a fundamental improvement that could really change how these AI models are built and used. This paves the way for a future where the answers we get from AI aren't just intelligent, they're practically instantaneous.